Hello, it's Keith here, and this is lesson 50 of the platform-specific series of my 68000 assembly programming tutorials, and we're looking at Mintile again, which is my multi-platform tilemap code. Now we're looking at the Amiga this time, so this is the Amiga version of the code, and if I find the right controller to control it, you can see we can move our character around the screen, and our code has X flip, so we can flip our character horizontally. The reason it has X flip and not Y flip as well is because this was written for a Z80 game called Chibi Fighter, and that didn't need Y flip. There's a version that's going to follow from Mintile known as Maxtile, which is far more advanced, and one of the more advanced things it has is it has the Y flip. So if you need something more, either wait for that or just add it yourself. Hopefully today's example will help you along the way. Now, much of the code for Mintile is multi-platform, so the 68000 code is shared in a lot of places, and that's got its own separate tutorial series on those parts. What we're going to look at today is the platform-specific parts, the parts relating to drawing the tiles to the screen. So this is a simple example of how to draw tiles quickly to the screen. Okay, so let's take a look at our code. Now, what we're not going to look at is we're not going to look at the parts that are multi-platform and the parts that we've covered in other tutorials. So we're not going to look at reading the joystick. We've discussed reading the joystick many times. There's a whole simple series example on that, and so we're not going to cover it again. Now, what we are going to discuss though is the VRAM, because we do have multiple options when it comes to how the VRAM is set up. Now, the way we've got the VRAM set up in this case is we've defined 4-bit planes, 16 colors, and basically each of these bit planes is about 40 bytes apart. So bit plane 0 is at offset 0, bit plane 1 is 40 bytes across, then bit plane 2, and then bit plane 3. And so to move an entire strip of pixels and all of these 4-bit planes, we need to add 160 to our line position, and we're going to see that in parts of our code. Now, our graphics data for our character is defined. We've got these bitmap data here. We've got some bitmaps for the background here, the same as the Atari ST format, and for our character. You can see our character moving around. That's the Chibico mascot for my website. So that's what we've got. And we've got these tile maps that are defined. This is the background tile map. A 0 in the background tile map means no change. The tile map for the background is actually a cache of changes. You see, Mintile is designed for limited 8-bit systems, and it doesn't use 2 buffers. It's not double buffering. That's because some systems simply can't do it. And so a 0 in here means no change, and anything else is a change to be written to the screen. This is the miniature tile map for the character. You see the Chibico character, the simulated sprite, is also actually a tile map. That's so we can use the same code for both jobs. So that's what we've got there, and that's what we're going to be drawing. Now, when it comes to the VRAM destination, if we're drawing the entire tile map, then we actually use the memory address of screen mem, and we're adding 4. The reason we're adding 4 is our virtual screen is 256 by 192, but that's smaller than the Amiga screen, so we're centering it by adding 4 bytes there. So that's the start of our VRAM. And when we're drawing the entire tile map, that's where we would start. But if we're drawing just a character, we actually need to calculate the position of that character, and we've got a routine called get screen pos, which will do that for us. Now, in all of my tutorials these days, I use logical units for my coordinates, and that means pairs of pixels basically. So, and the reason I do that is I need to have 1 byte coordinates for speed on the 8-bit systems, and I also need to have a 256 pixel wide screen use less than 256 for its maximum width, so that I have some coordinates that are off screen for cropping. So by using pairs of pixels as logical units, my 256 by 192 screen becomes a 128 by 96 logical unit screen, and that allows me to crop around the screen. So that's what we're doing here. Now, in this case though, what we're going to do is we're going to convert our logical units coordinates to a VRAM destination. And so what we're going to do is we're going to take our X coordinate here, and we're going to convert that to a number of tiles. Now, there's 4 logical units per tile, and so we're effectively dividing it by 4 here, and that is converting it to a number of tiles, and each tile is 1 byte wide, and so it's effectively an X offset in bytes here. So that's what we're doing. We are limiting the X positions to entire bytes here for speed. Not as neat, but that's what we're doing. I do have an alternate version of this code which uses the blitter, and that can do per pixel movement, so we'll see that next time. So that's our X coordinate calculated there. We're then taking our Y coordinate here, and we're going to effectively multiply this by the number of bytes per line. That's 40 times 4, 160. And then by 2, because we're working in logical units and we want to work in pixel lines. So that is effectively calculating our Y offsets here. We're adding all of those together to our screen base here, and that is calculating the VRAM destination in A6, and that will be done by the multi-platform code, which I've got a whole tutorial series on my website and on my YouTube channel. And what will actually happen when we want to draw an object to the screen is the multi-platform code will call a routine called doStrip. Now, whether we've got an entire screen or a little sprite, it's built up into horizontal strips, and so we would draw a strip and draw a strip and draw a strip and draw a strip, and we always work from left to right, even if the sprite is X-flipped. Okay, so doStrip will be executed, and we will have a pointer to the tilemap source data, the offset to the bitmap source data, the pattern data, the VRAM destination, and the width of this strip. And so what we're going to do is we're going to draw that to the screen. Okay, so we're loading in our tile number here from A2 here. If that's a 0, then this shouldn't be drawn to the screen. It's either an empty part of a sprite, or it's a part of the cache that hasn't changed, basically. Now, if it's not 0 though, we're going to check what we want to do, and we use the tile clear parameter to do that. If that is a 0, then we don't want to do anything. That means we're drawing sprites. If it's not 0 though, it means we're drawing the background tile map. We now want to 0 that because it's a cache of changes, and this change has been applied, or at least it will be very soon. Okay, that's why we do that. Now what we're going to do next is we're going to calculate the source pattern data. So we're taking our tile number in D0 and we're effectively multiplying it by 32. That's the source address offset for our pattern data for this tile. We're then adding A5, which is pointing to the start of the bitmap data in memory, and we're then going to add all that up, and that has now calculated our source bitmap data. We're then moving to the next source tile here, adding 1 to A2, and we're going to start transferring the bitmap data from our pattern to our VRAM. Okay, so what we're going to do here is we're going to basically have 8 lines. We're loading 7 into D1 because we're going to use a dbra command, and that will work for 0 as well. So a value of 7 in D1 actually runs 8 times. We're then going to transfer our source data from our source patterns in A3 to our screen. Now we're going to do the 4-bit planes. So the first byte here goes to the address in A6. The second byte goes into the address in A6 offset by 40. The next byte goes from A3 to offset 80, and then the final byte goes to offset 120. So this is the 4-bit planes. The memory layout in the source pattern data is these are consecutive bytes, and we put them to the correct positions for our VRAM. Now once we've done an entire line, we effectively add 160 to A6. That is moving us down, skipping all 4 of those bit planes to the next pixel line, and then we are repeating until we've done all 8 lines of our source pattern. So that's drawing a full tile to the screen. Okay, so now we're done. So we are then restoring A6. We backed up our VRAM destination, so we're now back to the original position at the top of the tile, so that we're then adding 1 to our VRAM destination, moving us across 1 byte, effectively 1 full tile. We're then repeating until we've done all the tiles in this strip, and then we return. Here we've got the empty tile code that is executed and just skips the tile if we didn't actually want to draw this one to the screen. So there we go. So that's how we're effectively drawing our patterns to the screen. Okay, so that's how we do our unflipped data. What about our flipped data when we want to X-flip the data? Well, one option for this on a system like the Amiga is we could simply have a second copy of all our tile patterns that have all been X-flipped. But on the 8-bit systems, that was never an option, and what we had to do is we had to use a lookup table to convert quickly that data. And so on the Amiga, I've done the same because I think it's a perfectly efficient way of doing things, so why not do it? So what we're going to do basically is we're going to define a 256 byte lookup table of every possible source byte and the X-flipped equivalent, and this works quite nicely on the Amiga because we're using bit planes, so that's what we're going to do. So basically we are going to use A0 as our pointer to our 256 byte lookup table, and we're going to use D1 as our source byte, and we're going to basically repeat until that goes over 255, and then we're done. And what we're going to do is we're going to take that source byte and we are going to take it and we're going to shift all of the 8 bits in that byte, and we're going to shift them out of the right of the byte and then shift them back into a new byte onto the left. This effectively flips all of the bits around. So that's what we're doing there. We're doing that 8 times, shifting all 8 bits of the source byte, and then we're writing the equivalent flip byte into the A0 here, and that is calculating the flipped equivalent of the source byte. Now this is now a lookup table that we can use quickly to convert our source data, and that's exactly what we're going to do. So we've got this do strip reverse version, which is an X-flipped version of the do strip routine. So first of all, we're loading in our pattern number, the same as before. We are then calculating the offset of our source pattern data. It's the same source pattern data. We're going to flip it. We're moving backwards through our source tilemap. We draw from left to right, but we go from right to left through our source tilemap. So that's what's happening there. And then we've got our loop again. We're going to draw 8 lines once again, but this time we're going to do things a little bit differently. Firstly, we've loaded A1 with the address of our flip lookup table. And then what we're going to do is we're going to load in a byte from our source data, our source pattern data, into D0, and then we're going to use D0 as an offset within that lookup table, the address in A1, that's our lookup table, and we're going to load that from our lookup table into D0. This is effectively the X-flipped equivalent of D0 because of how we built that lookup table. We then write that source byte to A6, the VRAM destination. So the first line is loading the unflipped data, the next line is flipping the data, and the third line is writing that flipped data to VRAM. Now, because of the way the bit planes work, we can do the exact same thing, just changing the offset each time, loading the 4 bytes from our source data. We then move down a line, repeat exactly the same as before. So that lookup table has done all of the work for us, and really there's not been too much extra code added. We were able to do things on a single line before. Now we have to use 3 lines, but that is still far better than trying to real-time flip, real-time bit shift all of those bits in memory, and it's also, generally speaking, going to be more efficient than having an entire set of extra pattern data. It might depend on how fast you need this code to be and how much memory you can spare, but I think overall I think this is the far better solution. And as I say, this is intended to be a 16-bit port of an 8-bit piece of code, so it's far faster than the 8-bit systems could ever dream of doing, so it's perfectly adequate for my needs. Anyway, you can go to my website and download the source code of the build scripts, and you can have a go with it, and if you can get anything out of it, you know, you're welcome to use it in your own projects, whatever they be, even if they're commercial. I really doubt you can use anything this simple in commercial code, but I just say it so you know. Anyway, hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.